the derivative, what we call the long way, right? F of x plus h minus f of x all over h, and we threw x cubed into it, and it came out 3x squared. It's like, wow, that's pretty cool. I mean, it's that easy, right? The slope of x to the fourth, you just bring the 4 down, drop it by 1. I mean, that gives you the slope. I mean, wow, that's kind of nice. And then, of course, we developed all the other rules. But again, the idea was, what's it go back to? The whole point of remembering that definition of derivative is keep in mind that all those slope rules go back, or all those derivative rules go back to slope. I mean, f of x plus h minus f of x, that's subtracting the y's. And h, that's subtracting the x's, and it's y's over x's, it's rise over run. It was a slope formula. So every time we use a derivative in the back, way back of your mind probably, but in the back of your mind is like, this all comes from slope. This all comes from the idea of slope. And likewise here, that when we do antiderivatives, right? When we do antiderivatives, which, you know, they come from area. Well, we saw yesterday, right? We have x plus 3, and it ended up being the formula for the area ended up being 1/2 x squared plus 3x, and then a c on the end, right? And it came from trapezoid of all things, right? So, and it's so not only does area have this kind of easy rule of finding the equation coming from geometry. Not only that, which is amazing enough, but not only that, it's the reverse process of what we did when we did slope, right? The slope formula. So how that all ties together, which is really why it became kind of an important body of math called calculus, right? I mean, I think what I told you at the beginning of the year is these were two individual kind of problems, among a lot of other problems that were being worked on in the day. Back then in the 1600s, in the Newton days, you had astronomy, right? That's where a lot of this slope stuff came from, was finding. I think I talked about this a little bit in optics. So with the telescope and those kind of things, it was, you know, you had this kind of stuff, angles. Well, you don't really do an angle with a curve. What you do is you have the angles of refraction, reflection, those kind of things. Well, of course, that angle is actually measured from what? The tangent line, a tangent line to a curve, right? And so these were the kinds of ideas that were being worked on that led to the derivative part of calculus. So that thing. And then, like we were talking about, well, I think maybe I mentioned this in the other class yesterday, back in those days, the people that were rich, kind of the rulers, those people were the property owners. I mean, that's really what was of value in those days, was property. So knowing how much property you had was a big deal. And so if you had a piece of land surrounded on one side by a river in some weird shape, knowing what this area is, this kind of strange area that's not a geometric shape, was a big deal. And so different ways of estimating and approximating that area. And it was in the study of those two things that guys like Leibniz and Newton and those guys came up with these things that ended up being connected, and then the connection of them, and then all the uses. And a lot of the uses that we use now have come from it, weren't even envisioned back then, right? I mean, so you get into the optimization kinds of things, and the matchman and some of those things that we'll learn later here about integrals. So it was all of that stuff that kind of came from it that made it a big deal, right? And so the connection of these two things is the big deal, right? And that's what we're studying right now. And it's called, in that worksheet, it was called the fundamental theorem. Fundamental theorem of calculus. I mean, that name even sounds like a big deal, right? The fundamental theorem of calculus, right? And what it is the connection here. So we're going to dig into the weeds here a little bit for a day or two, kind of like we did doing the long way. Show you a little bit of a shortcut with it, but you are going to, on your homework tonight, you are going to be drawing some pictures here and doing some areas. Okay, so we're going to run through. I'm going to do an example for you that's just like the one you're supposed to do, so you can use that as a guide. Okay, so and it's a little bit like number 2 here. So number 2, you were given this information, and like yesterday I said, I would just probably do it this way. I would take my function x, stick it in here, but I got to put a t there when I put it in there, right? So here's a picture from 4 to x. That's going to be a trapezoid. So take out number 2. What did it say? It just said find. Show that, they said show that big A is equal to 1/2 x squared minus 8. Okay, so they told you what you're supposed to come up with. They might have just said, find big A of x, right? That's probably what I'm going to ask on a quiz. I might say, draw a graph, use that to find big A of x. Okay, so we know, I mean, I'm looking ahead just a little bit, but we know it's going to be that, right? Because it's going to be the antiderivative, right? I mean, never lose sight of the big picture here, that this is little f and this is antiderivative. So again, big picture is what's going to be important for us going forward. When we see area function, when we see a number and an x up here, what's the first thing we think? Antiderivative. You think area, but then you think antiderivative. So you see the area function, right away you think that's the antiderivative of little f. That's what that represents. Okay, that's the connection we made yesterday. Okay? All right. So, we know it's going to be this, right? Just like when we were doing them the long way, when we did x cubed the long way after we learned it, we were doing x cubed the long way, you knew it was going to come out 3x squared, right? But we still went through the process, okay? So we're going to do that here. All right, so this is a trapezoid, so it'll be 1/2. What's this base right here? This base, this trapezoid, that's 4. What's this base? X, because the graph is y equals x. You put an x in to get an x out. Okay, and then this width right here, x minus 4, right? So this is, then we flip that around to x plus 4, and so that's going to be 1/2, and that's going to be x squared minus 16, right? And we're going to get 1/2 x squared minus 8, which is what we were supposed to show. That's it. Okay, now that's a pretty simple one. Okay, might be a little more algebra in another one that we'll get into later, but that shows us. So that found the, and we said that this was the C, right? And what determined the C? The 4, right? If we put a different left endpoint into this, we would still get 1/2 x squared, but we get another difference there. And what would be the difference between the area from 4 to x and the area from 5 to x? What's the difference between those two? The area from 4 to 5, right? The difference between the area from 4 to x and the area from 5 to x is that piece of area from 4 to 5. That is going to be the difference in the C values of those two numbers, or those two functions, right? That's why it's a constant, because that's a fixed piece of area, that area from 4 to 5, the difference between those functions. Okay, so let's go. Now, this is one of those assignments, just like early on, we're chapter 1, where some of those assignments I went through in great detail, and maybe you got all these answers right, and it was no problem. Okay, but I really want to talk about it, because remember, now that we're talking about the chart, before the chart was all about slope, but now we realize it can be about area too. So I want to talk about it in those terms. Okay, so here we have this function little f. Okay, and so 3 says which is larger, big A of 1? Oh, okay, and by the way, big A of x is the area from 0 to x, right? So big A of 1 or big A of 5, right? So, how did you think about this? How did you think about A of 1? I think what's going to happen when we go through 3 through 8 here, I think what's going to happen is you're going to learn some things about this that didn't cross your mind when you were doing this process. Okay, that's why I'm going through, so be careful. What did you think of when you saw A of 1? Area from 0 to 1. Area from 0 to 1. Okay, so right, 1 box, 2 box, 3 box, about 3.5, whatever. And then A of 5 is area from 0 to 5, which is bigger? A of 5, easy. Now, let's think antiderivative. Let's think the new thing. That's little f. What's big A? What's big A compared to little f? Antiderivative, right? Antiderivative, that's what we just said a minute ago. Big A, when you see this, big A is the antiderivative of little f. Okay? Oh, so wait a minute. Isn't this just like those chart problems? So what's little f compared to big A? The derivative, right? So this is like one of those problems where we got there. So now let's think of slope. So this graph is the what? Slopes of A. So now let's compare. Which is bigger, A of 1 or A of 5? Well, apparently the same answer. The answer was A of 5, right? Why? From a slope perspective. What's increasing? Don't say area. I don't want to talk area, I want to talk slopes. What? Yeah. the slopes are what? Not increasing. Careful, positive, right? This is the derivative graph, right? It's above the x-axis, right? So little f is positive, therefore big A is increasing, right? Just basic chart stuff. Little f is positive from 1 to 5, so therefore big A has to be increasing from 1 to 5. So what's bigger, A of 1 or A of 5? Got to be A of 5. You see what I mean? If I would have asked this, if I wouldn't have put this up here, and I just said, called this f prime, and asked you, is f, what's bigger, f1, f5? You just thought of slope, right? Okay, so that's what I want to get your mind around here, is that we can think of as area, we can think of as slope, right? And they both work. And again, reinforcing the idea that this area function is the antiderivative, so all those same connections that we had in the chart still hold, okay? I'm not saying you have to give both reasons, right? My guess is on our next quiz, which is probably Wednesday, that you will probably use area reasons, because that's kind of what we're talking about. And that's what you'll think of, and that's fine. I think that's good. Some of the problems are easier to do. There was a problem, and when I passed back your package, there was a problem I told you where we had to find, we were given a derivative graph, we were supposed to figure out what the max was of the antiderivative function. And I told you this will be easier when we learn about areas. And that's what I'm talking about. In that problem, you can think about it as slope, but it'll be easier if you can think about it as areas. Okay? All right. 4. Which is larger, A of 7 or A of 10? What did you say? A of 7. Now again, if you think area, what happens? A of 7, you got a bunch of positive area, a little bit of negative. But then when you go to 10, you're going to, from 7 to 10, you're going to pick up what? More negative area, right? You're going to pick up, when you go from 7 to 10, you're going to pick up more negative area. So therefore, the area will be less. And so A of 7 is going to be bigger. Or you could say what? The slopes are negative, so what's the big A graph doing? Decreasing. So therefore, A of 7 is going to be bigger than 10. Explain why A of negative 1 is negative. A of negative 1. Well, that'd be the area from 0 to negative 1. You're going backwards. So therefore, any area above the x-axis has to be negative, opposite. Okay, 6. Is A of 8 positive? That's the area from 0 to 8. Sure, because there's way more positive area to offset that little bit of negative. But what if we were talking slope? Think of the midterm. I think on that other midterm, we had a problem like this. Since the slopes are positive most of the time, right? The graph is increasing most of the time, and then until 8, and then it decreases a little. So it's going up, and it's positive, way positive, and then it goes down a little. So it's got to be positive, right? What do you think of slopes? We think area. But the area is more convincing because, slope, remember some of you didn't get the point credit on that one because you just said, well, it just increases for a long time. But now we can actually say, look at this. It's obvious. Look at all this area. Way offsets that piece of area. Okay? A of negative 2 or A of negative 1, which is bigger? A of negative 1, because when you go backwards, you're picking up what kind of area? Negative. So you pick up negative area to there, and you pick up more negative area, it's going to be farther down, right? So A of negative 1 is going to be bigger. Or, think of slope, what's this graph doing from here to here? It's positive the whole time, so that graph's got to be going up. So A of negative 1 is got to be bigger than this one back here, A of negative 2. If we were thinking about slopes, we would have thought of it that way. We would have thought left to right. With area, we were thinking this way because of the way it was given, but same answer. Okay. All right, 8 is, let big F be the area from negative 2 to X, so different left endpoint. Explain why big A is equal to big F plus C. So what I want you to understand about that statement, because you're going to see this a lot, big A is equal to F plus C, so big A of X equal to, all this is saying that these two functions are the same except for some constant. So that's what we often talk about with derivatives. Antiderivatives of the same little f. We write it like that. And that just says, hey, they're the same except for some constant. Okay? But then this one goes a little deeper and says where C is negative. Why is C negative? Well, the area from 0 to negative 2 is, right, negative. Okay, so that's why. That's the difference between those two, is that piece of area. And big F is the one from -2. So it's going to have more of this area. Another way to think about that would be this. If you take big F, which would go from -2 this way, and you take big A, which goes 0 this way, you could say, well, big F will have some positive area that this other one won't. So big F is actually bigger, right? Would you agree with that? Big F would actually be bigger. Well, so if these two are going to be equal, but big F is bigger than big A, then what's C got to be? C's got to be negative for those to be equal. That's another way to think about it. Okay? So big F goes from here on, big A goes from here on. This one's going to have some extra positive area because it's going that way. So for those to be equal, you better take off some. That's why C's negative. So you can explain that. Okay, so let's look at the next group. Big F is from 0 to x, big G is from 5 to x. So again, these are both antiderivatives, just the C is different because the left endpoint's different. Suppose that little f is above here, so little f's up here somewhere all the time. Little f's always up here. Well, what's that tell us? Think slope, right? Think slope right away. What's big F and big G doing? Little f is a derivative, right? So if it's always above 1, that means these graphs are always increasing, right? The area is always going to be positive as we go this way, right? So 9 says, why is big F of 7 greater than big F of 1? So that just looks at that. Well, that'd be the area from 0 to 7 compared to area from 0 to 1. Well, it's more area. It's positive area because little f is there, so that's pretty easy. 10, is big G of 9 bigger than big G of 5? Well, big G of 9 would be the area from 5 to 9. Big G of 5 would be the area from 5 to 5. Which one's bigger? 5 to 9. That's pretty easy. Okay? And then explain why big F of x is greater than big F of 0 for all x greater than 0. So big F of x, which is the area from 0 to x, why does that area have to be greater than big F of 0? What's big F of 0? 0. Now it says for all x greater than 0, so that's just going to the right. So that's actually pretty easy too. So those weren't too bad. Okay, so this area has got to be positive, and that's because the graph's always above 1, always above the x-axis. So as we go to the right, the area is always going to be greater than 0. Okay, always going to be positive. But so that's just a little bit getting used to the notation. So the ideas weren't too hard on some of those. Getting used to the notation is kind of what we're after here. All right, so that was it on the homework. Okay, so let's go to your notes, and this is what you're going to have to do for part of your homework. Okay, and we're going to run through this problem, and we're going to write down the fundamental theorem, what it actually looks like, and then we'll let you go to work. All right. All right, so this is a series of exercises, 21 through 28, and 21 is by far the longest part of all those. 22 and 23 we'll just do real quickly, just talk about them, and then part of your homework you'll go from 24 through 28. Then you're going to do 29 through 36, which is the same set of exercises, just with a different function. So your 29 on your homework is going to look just like what we're about to do here. Okay, so your 29 on the homework is going to look just like what we're doing right here for number 21. And then the rest of the questions go pretty quick. They're just chart questions basically on that. Okay, so 29 is going to be the important one. If I come around and check homework on Monday, I'm going to be looking for number 29. Okay, because it's going to have 3 different pictures, one for F, one for G, one for H, okay, and so forth. Matter of fact, I'm going to get 3 pages in here. All right, so we're supposed to find, so 21 it says find formulas for big F, big G, and big H. Okay? All right. Now, I am going to show you, we're going to go kind of the longer way. I'm going to show you a little bit of a shortcut then, okay? And then I want you to do the longer way on the homework, okay? But that's really the only problem with homework that takes much time. The rest of them are pretty much chart kind of questions and thinking about notation. So here's our little f. So these functions, so I could put a 3t plus 2 in here, right? I could put 3t plus 2 here, 3t plus 2, 3t plus 2 could be here in place of the f, right? So they're all, right, they just have different left endpoints, okay? All right, so the first one's pretty easy. It's going to be the area from 0 to x, okay? So let's put our x over here somewhere, and it's a trapezoid, right? So there's our area from 0 to x. So what do we got? We got 1/2. What's this height right here? 2. This height right here, not x this time. That was only because it was y equals x last time. This point is x comma 3x plus 2, right? xy, x comma y, and the y is 3x plus 2. So that height over here is 3x plus 2, okay? So 3x plus 2. And then the width here, that's x minus 0, right? So this width right here is x minus 0. So we got 1/2, 3x plus 4, actually 1/2 x. Let's bring that x around with 1/2. So let's distribute. We got 3/2 x squared plus 2x is big F. Okay, any surprise there? No surprise, right? Because little f was 3x plus 2. Right? Little f was 3x plus 2. So the antiderivative would be raise it to a 2 divide 3/2 x squared plus 2x plus some c. Well, our c is 0. So the only surprise was we didn't know what the c was. Right? That's the only surprise. So we ended up with 3x squared plus 2x, and there was no c. Okay, fair enough. All right, now you can draw. I really want you to have on your homework, I really want you to have 3 pictures because it'll get to be a mess otherwise. Okay, so this, now it doesn't have to be fancy, just draw an XY axis, draw a line through there, right? Doesn't have to be real fancy. Okay, because now we're going to do G. Now we're going to do G. Okay, so G is the area from 1 to x. Right. Now you might say, okay, we already did big F. We know it's going to be 3/2 x squared plus 2x. What we don't know is the c. And what's the c going to be here? Or the difference between the c in the last problem and the c in this problem? The area from 0 to 1. So I suppose you could say, well, we could just find the area from 0 to 1 and then throw that on to this function. Okay? Now, if you did that, would it be a positive c? Would it be a plus that number, that area, or would it be a minus? This function has more or less area? Less area, doesn't it? So wouldn't you take that 0 to 1 and minus it probably? We'll do that. I would. That's not really my shortcut here. I guess it might end up being a little shorter once you've done 1. So, but let's talk about it. Let's just do it our normal way here. So what is this height right here? 5. You put a 1 into that function, you get 5. And what's this one over here? Still 3x plus 2, right? You plug a 2 into there, it's still 3x plus 2. So we're going to have 1/2, still a trapezoid, 5 plus 3x plus 2. And now what's our width here? X minus 1. So we're going to have 1/2, we're going to have 3x plus 7, we're going to have x minus 1. So we're going to have 1/2 3x squared, 7x minus 3 would be 4x, and then minus 7. So we're going to have 3 halves x squared plus 2x minus 7 halves. And that's going to be g. Okay, so we just do it. I want us to do it as an area, but if we look at this area, this would be 2, that's 5, that'd be 1/2, 2 plus 5, times a width of 1, that would be 7 halves. So the area from 0 to 1 is 7 halves. So that doesn't mean that's the C, that means that's the difference from the last one, right? But the last one didn't have a C, the C was 0. So that means this one's going to have 7 halves less than the other one. So if the other one would have had a plus 2 at the end, we'd have had to do plus 2, take away 7 halves, understand? So it's the difference between 0 to x and 1 to x, okay? But again, not really going to be a huge factor going forward doing that, but just from an understanding, the concept standpoint, that's a good thing to know. Okay, one more. Okay, one more. So again, antiderivative. Again, amazing how that worked out. Comes from trapezoid, comes from just area. All right, -2. Now this crosses back here at -2/3, and that hasn't been a factor, but it is going to be a factor now because -2 is over here. Okay, so now -2 to x. Now I'm going to put my x over here. I suppose you could argue that you could put the x right here, and that might simplify things a little bit. Maybe, okay, but I think I'm going to put the x over here, okay, just to keep it the way it's been. So now what I've got, I just want you to show that it could be, different geometric shape you end up with, which is 2 triangles here, okay. So this triangle's fixed. Let's just imagine x sliding around over here, okay. So this triangle is just fixed, right? So what's this distance? Well, from -2/3 to there, what's that, 4/3? And what's this distance here for putting -2 into there? -4, right? Now this piece of area right here is positive or negative. That's negative area, right? Remember, we're going from -2 to x. So we're going this way. So that's going to be a negative piece of area. So 1/2, well, let's just put it up here. So h of x is going to be negative, and then we'll go 1/2 times 4 times 4/3. We just know that's going to be a negative piece of area. Okay? Plus this triangle. 1/2, what's this right here? X plus 2/3, be x minus a -2/3, right? So this would be x plus 2/3, and then this height right here, 3x plus 2 again. Okay, so let's go here. That's going to be -2 times that. That's going to be -8/3 plus, and then this is going to be 1/2, and this is going to get a little messy with fractions, but we're going to have 3x squared. Then we're going to have, oh, not bad, 2/3 times 3. That's good. 2/3 times 3 on the inners. That's going to be 2x plus 2x. That's going to be 4x, and then 2/3 times 2 would be 4/3 at the end. So we're going to have -8/3 plus 3 halves x squared plus 2x plus 2/3. 1/2 times 4/3 would be 2/3. And we add the 2/3 to the -8/3, and that's going to be -6/3 or -2. So at the end of the day, h of x is 3 halves x squared plus 2x minus 2. Okay, so that one is kind of in between the other two because this one has more negative area, but that's got a little more positive area too, and so it ends up being kind of in between as far as the C. All right, so on 29, I want you to do that. On homework, yeah, but they give you a different little f, same big F, big G, big H, and you do those three. Let's see the work, and let's see it come out for area. Okay, so that's kind of your guideline for number 29 today. All right, now I'm going to show you a shortcut in a second. So 22 says find the number C since that big G is equal to big F plus C. So at 22, you want big G to equal big F plus C. Okay, well, let's compare big G and big F. So big G had a 0 here. and big F had a -7/2. So which one of those is bigger? This is what usually makes sense to me. Which is bigger, big F or big G? Big F, because big G had a -7/2 at the end. So to me, big F is bigger. See, because I could have wrote this F equals G plus C, and then the C would be opposite, right? So the point here is trying to get the sign right. Okay, so big F is bigger. So what's C got to be to make these equal? Negative. So the C would be -7/2. So to answer question 22, find the number C since a big G is equal to big F plus C. We'd have to take big F, subtract 7/2. That would make it equal to big G. If those were switched around, it would be a plus 7/2. It would be positive 7/2 for C. Okay? So you might jot that down because that's, well, I guess you're going to answer that in a later one. That's not part of it. And then find a formula for big F minus big H. Well, big F minus big H, the whole point is if you take big F and you subtract this, the X's are all going to disappear because they're the same. So when you subtract them, so all you're going to have are the C's. You're going to have 0, take away -2, which is going to be positive 2, right? But the whole point of both those questions is saying, you know what, the only difference in those is a constant. So it's this aha moment, right? I mean, which we've already had. But that's the whole point of kind of these problems. Is, oh my God, yeah, the area is antiderivative. Okay, enough of that. We got it. Here's a shortcut. Okay, so you take little f, or let's just say, let's take G. Okay, so big G was the integral from what? What was that one? 1 to x of 3t plus 2 dt. So let's say I just give you that, okay, which is what I gave you for this problem we just did. So and I say, find a formula for big G of x. Okay, so that's what we just did. So the long way of doing that is draw a picture of little f, find the area from 1 to x, and there's your formula. Okay? So I want you to be able to do that, number 29. Now, we get to the quiz on Wednesday, probably not going to have to do it. Okay? I know when we did the long way derivative-wise, I made you use that limit definition and so forth. Probably not going to go through that. Now, I may give you a picture with a trapezoid and do this and say, find the formula for this area. And then you would have to do it, right? But not doing it from scratch. If I just give you this, I would say, okay, you can use this shortcut. So what's the shortcut? Well, we already know big G is going to be what? Part of the formula is already going to be what? The antiderivative, right? So let's just do that. So we already know. Now remember, when we write it, are they going to be T's or X's? They're going to be X's. We already saw that happen. They were T's in here, but it didn't matter. They were X's here. Why were the X's here? Because we had this X over here. We had this right input that was X. When we plug it into the function, if that has a T or a W or a Z, it doesn't matter. We plug an X into it, it's going to have X's. So that's a mistake sometimes people make. When I give them this problem and they do the antiderivative, they do this. Right? And you don't want to do that. Right? You don't want to do that. It's going to be X's. So that's one thing you got to keep in mind. The whole reason there are T's in here is just because we can't use X's. But down here, look at that variable right there. They got to be X's. Okay? They got to be X's. Okay, so it's going to be 3/2. So this part we know. It's going to be 3/2 x squared plus 2x. And that's going to be plus some C. Okay. How do we get the C without going through the whole process of drawing the arrow? Think about differential equations. They often have a plus C. How do we find the plus C? What did we need? A known value, an initial condition. If we knew just one value on big G, that would do it for us. And I say we do. Which one do we know? We know G of 1. We get a free initial condition. We get a free initial condition in this area formula. We know that G of 1 is 0. Okay? They didn't have to say it. We just get it for free. So G of 1 is 0. So we're going to put a 1 in. And that's got to equal 0. So this becomes 3/2 plus 2 plus C equals 0. 3/2 plus 2 is what? 3.5, which is -7/2. C is -7/2. And that's what we got. free initial condition. Anytime you get this area function, you get that right there. Okay? All right. So we could do that for H, and so on the homework, you can do that to check. I want to see your picture. I want to see your area calculations just this one time. Okay? But, after that, we can look at it that way. Okay? All right. So, finally, just summarize this up. Let big A equal the integral from little a to x of little f of t. What's the connection between A and F? A is the antiderivative of F. Now, here's the problem. How do we say that without having to write that out like that all the time? It was easy for us with slope. We just had this notation called prime, right? F prime is if F was a derivative of G, we just called it G prime, right? And that was our notation. So how do we say it? Well, how did we check? Remember when we did our just simple antiderivatives? How did we check that we got that it was the antiderivative? How do we check it? Do the derivative. I always told you, I said, if you're not sure if this is the antiderivative, do the derivative and see if you get back to what you started with. So that's how we're going to say that something's the antiderivative. We're going to say it this way. Here's how we say it with notation. The derivative of A of x is f of x. That says that big A is the antiderivative. The derivative of A of x is equal to f. That is saying that A is the antiderivative of f. We don't really have a symbol for antiderivative. I guess we have this area symbol, but that means area. That's the integral. So we got to understand. If we're doing a fixed area like from 2 to 7, that's not antiderivative. That's just a piece of area. Okay, it's this area function when we have the x up at the top that it becomes antiderivative. So the way we say it, the derivative of big A is equal to little f. Now, let's take this. So the way this is formally written then is we take this and we're going to sneak it right in there. So the way the fundamental thing, because that's what this is. This is the fundamental theorem. This is the connection. This is the connection. Because this line says a mouthful right here. Because this is area and this is slope. And this is basically saying that those two undo each other. That's the relationship. That's the connection. So this line says a lot. That's your connection from area to slope right there. Okay? So we're going to sneak that in there and we're going to write it like that. Okay? And that is called the Fundamental Theorem of Calculus, Part 1. Part 2 is going to be when we say, okay, can we use this information? This is what we're going to learn next week. Can we use this information to help us find areas now, like under x squared, under a curve that is not a geometric shape? Can we use this information to help us find areas? If the area function gives you the area at various points, and the area function is the antiderivative, it would make sense that the antiderivative could be used to help us find areas under all kinds of functions, as long as we can do the antiderivative. Okay? And so that's what we're going to do next. That's going to be part 2. But part 1 is just the connection. Okay? The derivative of the area function gives you back little f. Now notice it's got little f of t in here, but when it comes out, it's little f of x. Okay? And again, that's because of that work we just got done doing earlier, where we did it, and we did the areas, and it came out with x's. Okay? The easiest question, I'm going to tell you right now, the easiest question is going to be on the quiz on Wednesday. I'll just give it to you. It's not going to be, this won't be the exact function that I'll give you, but oops, hang on, left something out. That's going to be the easiest question that I will give you on the quiz on Wednesday. What's the answer to this? Cosine e to the 7x. That's the answer. That's the answer. Why is that the answer? Because this is the area function. The area function means what? Antiderivative. So somehow, but guess what? Here's a little, let you in a little secret. There is no antiderivative to this, so that's something we'll have to deal with over the next couple of weeks. There is no antiderivative, but who cares? Because this is saying, hey, this is the antiderivative of this thing. And the 4 does what? What's a 4 give us? Some plus c, right? So there's some antiderivative plus some c, but then you're going to do what to it? You're going to do the derivative. Well, what's going to happen if you did if you even could do the antiderivative, what's going to happen when you do the derivative? You're just going to undo it. It's like the square root of x squared, right? So this is saying do the antiderivative of this with some c, but then when you do the derivative, you're just going to get back to this, and what happens to the c? It goes away, right? We do the derivative, the c goes away. So we don't even care about the 4, right? We don't care about the 4. If this was a 7 or a -2 or whatever, it'd still be the same answer, because the c would go away. So this is saying there's some antiderivative with some c, then do the derivative, you get back to what you started with, and the c goes away. Except what you get back has not a t in it, but a x. And people that miss it are going to try to do a derivative here, an antiderivative, or they're going to put a t over there in their answer. And that's going to be wrong. That's probably worth 1 point, but I'm going to give you a problem like that. That's right. So this is more of an idea. This is not really a formula we use for anything. It's more of an idea. It's saying that the area function is the antiderivative. That's what it's saying, which is a lot. But part 2 is going to be more useful as an actual formula to use. Okay, but like I said, I give you that. That's the answer. All right. So for homework, so 12 through 14 is a little more of the chart stuff that just takes off from where we left off. 24 through 28 is more chart stuff. That's from this stuff that we just got done doing. They're going to ask you about big G and big H and where is big G increasing. Well, big G is increasing. It's the antiderivative. So big G is increasing when its derivative, little f, is positive, right? I mean, that's going to be easy. So you just look at the graph and, right, just chart question. Chart question. What you'll know is it doesn't matter if I ask you about big F, big G, or big H, right? Now, well, hang on a minute. Hang on a minute. Let me clarify that, because I'm not sure everybody's going to be on board with that. Big F, big G, and big H. Where's a local min of big F? Where's the local min of big F? Where? -2/3, isn't it? The local min of big F is at -2/3. Why? Because little f is the derivative of that. And that's where little f, the derivative, goes from negative to positive. Where's the local minimum of big G? Where's the local minimum of big H? Really? They all have the same local minimum? Doesn't the plus C make a difference? Oh, what's a plus C do to big F, big G, and big H? It does this. Does that change any of the chart stuff? Does that change where your local maximum is? Does it change where your flex point is? Doesn't change any of it. It changes their y values, but we never ask about those in the chart, right? We only ask where. Yeah, so big F, big G, and big H, if we were to graph those, they would all just be vertical shifts, right? Remember the sliding thing the other day? It just went up and down, right? You change the left endpoint, just goes up and down. So you see what I mean? So all those questions, so 24 through 28 should be easy if you don't get confused by all the stuff, all the left endpoints and stuff. But the left endpoints don't matter. They just do this. So that doesn't change the chart stuff. Okay. Anyway, so 24 through 28 is some chart questions. The 29 through, so 29 then is where you repeat what we did on those three, big F, big G, big H, and then you answer those same chart questions. Okay? All right. Rest of the time.